What is the gain of a system? What do we mean with gain? Let's go here. Let's go here directly. Definition from an intuitive perspective, caveats on the use of the final value theorem, and we do some examples. So, in generic terms, the gain of a system is something that applies to the steady state behavior. We assume to be in steady state, we make unitary step, and the gain is how much y deviates. Let's make it graphically. Time, I am in steady state, and this is my y, and I have a u that is like this one, and then I do a step, and this will do something, true? And for this injection, we get this gain. What is the gain? I put a delta u, and I will get a certain delta y. And the gain is going to be this ratio. This is going to be my gain after the detransient passed. I put 1 Newton, I move of 10 meters. I put 0.5 Newtons, I move of 30 meters. The gain is essentially how much you amplify the input or make it small. Are we together? Do you see it from a practical perspective? Hmm? So, whenever we talk about LTI systems, we have superposition effects. True? So if I have this leads to this, if I increase it everything of 5, this is increasing of 5. True? The ratio is going to stay independent. In LTI systems, whenever we talk about gain, is the ratio between the deltas. And if I have 3 times the u, I will have 3 times the y. That means that the deltas are going to stay the same. The ratio, delta u, delta y, but delta y, delta u is the same, is independent of the actual u. Something that is not valid for nonlinear systems. And indeed, for nonlinear systems, defining the gain is much more difficult. For linear systems, LTI systems, it's very easy. Nonlinear systems, it might depend on the u that you're using. How much are we together on this, people? Excellent. Well, perfect. So, how many of you heard about final value theorem? I am a final value theorem. Never heard. Kind of heard, but I'm not sure about it. I see several twos and few threes. Let's do it in this way. For continuous time systems, final value theorem is this one. As soon as this one exists finite, if this one if this one exists finite, the final value is this limit here. Let's apply it. I have s plus 3 divided s plus 2, s plus 4. This is my f, y of s. By looking at this one, tell me this. Without computing this. This is going to be equal to, you've got to find it by just looking at where the both are. Yeah. This one looks like this one. Those modes go to 0. This amplifies the modes or diminishes the modes, but they are going to zero. Everything goes to zero. True? Indeed, if we look at this stuff here, we are going to have that this object is this times s. Take this one and do the limit that goes to zero. This one goes to zero because this one goes to zero. True? You see it? Are we together? Perfect. Now, let's take y of s equals to this object here. This one, does it go to zero as before? Yes, no, I do not know. Just look at the position of the poles. Where does it go, people? Does it go to zero? No, very much no. Why? Because somehow from a pole's perspective, it's this, this. True? If we think in modes, goes down, this one does like this. True? Perfect. So essentially, it's going to be doing something in time for which does something and then it stays at somewhere. How high? How do I compute this height? I apply the final value theorem. Does this limit exceed finite? Yes, indeed. And I compute this value here. Let's call it star. Let's call it star. Is going to be equal to what? Star is going to be equal to this times s, this limit for s that goes to zero. That means these and these disappear, 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 disappear. How much does it go? To 3/8. Okay? 3/8. If here I was having 1/8. Let's relook at it. Cross, 0, cross, cross. What did I do? I moved the 0 from here to here. What is the fact? The mode associated to these, the residual associated to this mode becomes smaller. Do you see it? How do you see it? How much do you see it, people? 1, 2, 3. Here I move the pole. True? Sorry, the 0 from s plus 3 that I was having before. I move the pole here, the 0 here. The mode associated to this pole is in any case a step. The gain is going to be eventually the amplitude of this step. True? If we go computing via the final value theorem, in this situation, the gain is 1/8. In this situation, the gain was 3/8. Those ones are essentially the residuals associated to this pole. And by making the 0 get closer, the residual associated to that mode goes down. Do you see? Excellent. S minus 2 over S minus 4. This is my y. Okay, this is my y in Laplace. Can I apply this object here? Can I apply the final value theorem? I can apply, cannot apply, I do not know. Discuss? Can I apply the final value theorem in that situation? People, this stuff here, how does it look like? This stuff here looks like one here, one here, one here. True? This stuff here, how does it behave? Explodes. True? Do we have a limit that exists and is finite? No, for sure it's not finite. I cannot apply finite value theorem. Indeed, it goes to infinity. True? Perfect. Can we apply the final value theorem to a y of t that looks like this one? 1 over s plus s squared plus 7 squared. Can I apply final value theorem to this? Yes, no, I do not know. What would you say, people? What would you say? This one is a cosine, true? A cosine, what does it do? Oscillates forever. Does the limit exist? No. Cannot apply final value theorem. Okay. Now, let's see if you see it. I have an impulse response that looks like this one and oscillates forever in time. Will we have finite, how do you say? Given this age, how do I compute the step response? If I give you this one, this is this one. How do I compute from this one the step response? Discuss. The step. What is the step with respect to the Dirac delta? The step is what with respect to the Dirac delta? The step is the integral of the Dirac delta. So this one, what is it going to be with respect to this one? The integral of that stuff there. True? Linearity. Are we together? Are we together? Are we together? Where do we see the gain of a system? We see it in the step response. True? We apply a step and we see what comes out. True? See, stability is very important. Stability. By the way, I'm talking about stability. People stable, this one? Yes, no, I do not know. This is unbelievably unstable. True. This is like, look at it. It's kind of very unstable. You got non-integrability, non-absolute integrability. Anyway, let's go back to our step response. Step response, from the step response, we see the gain. But in this case here, this one, is it going to have a finite limit? No, because the integral of that stuff here is going to explode. True? Are we together? Perfect. Now, are we together that this one, starting from this one, the blue one is going to do something like this? Do you see? Perfect. If I take now, so we cannot apply final value theorem, we cannot apply the concept of gain because that stuff there that diverges. We are together on this one, 1, 2, 3, true? Perfect. Now let's change h of t, let's make this h of t. Okay, this is my h of t now. Vivo stable? Yes, no, I do not know. No, why? Absolute integrability. This one is not Vivo stable. Okay? Are we together? This is not Vivo stable. So this is not Vivo stable. Is U equals to step, for this case, a bounded input that leads to an unbounded output? Yes, no, I do not know. There is not a Vivo stable system. But I give a step and I look at the step response. Is the step response going to diverge? Yes, no, I do not know. Discuss. What would you say, people? What would you say? No, people. If I take the step response, if I take U equals to step, what does the convolution with a step do? It's the integral, true? And if I do the integral up to here, up to here, up to here, up to here, the step response is going to do something like this. You see it with the same frequency, actually, but you got the point. True? Hmm? Indeed. Let's think at h of s. How does h of s look like in this case? Probably you don't see it. I don't know. I hope you see it. We are going to have something that looks like an exponential that does like this, double quote, plus a cosine that stays there. Together, you see, 1, 2, 3. Excellent. If I do a step response, what am I taking? I'm taking basically u equals to here, and then I'm going to take the Laplace of everything here. Does that stuff explode? No. It's going to do something that looks like this one, so as we were saying. Are you seeing it? Perfect. Can we define the gain? In an average sense, yes, but actually the definition, no, because we have something that is oscillating from each oscillating. We do not have must exist and finite. True. Something that oscillates doesn't have a limit. Are we together, people? What's the thing? And this is an interesting theory. How to compute the gain associated to a transfer function, assuming that it's Bibo, assuming that we can actually use the final value theorem. We take y of t, we take this stuff here. This stuff here is this stuff here. But actually, we are applying the step, and the step goes eating the s that is in the definition of the final value theorem. What remains for the h's for which we can define the concept of gain, h of 0 is the gain. But only if h is such that I can use the final value theorem. An h that looks like this one. Can I apply this concept here? No, because it's this one. Are we together, people? 1, 2, 3. For an h that looks like this one, can I apply this concept? No. For this one, yes. How is the gainer related to the Laplace transform? This one is h of 0. What is h of 0? Is the height of the blanket is 0. You see? Together? There is going to be a real number if you've got a real system. Very much together, not at all, kind of. Where are the doubts, people? I see something good. Are there questions? Yes.
Just a clarifying question. When you plotted the graphs on the other slide, is that like the response to the theorem? What's the red one? What is the response to what is it?
That is the impulse response.
Yeah, impulse response. Yeah.
Okay. And this is going to be the step response.
Yeah.
Okay. They are connected. Impulse response, it has to be Dirac delta. Yeah. It is the impulse response. Step response, a response to the step.
Yeah.
What is the step? It's the integral of impulse. The step response, if I have the impulse response, the step response is the integral of the impulse response. And if from a physical perspective, I derived the ramp response, how do I do numerically to go back to impulse response? Derivation, derivation. How much are we together, people want to think? Are there other questions about this? Fine. This one, gain here, gain for this, s equal to 0, 1/2. True? But I can apply, okay? Okay? The proof is trivial. Don't even want to go through it. It's so trivial. Okay, so final value theorem. Where do I go? This one is going to be equal to discuss and with the fingers.
No, it's 0.
Okay, so from the voices that I hear, there's a little bit of confusion. Let me clarify. We saw two concepts. We saw final value theorem, and we saw also the gain. Final value theorem is I have a signal, I take the signal. If I can apply the final value theorem, I multiply times s and I evaluate in 0. Okay? This is the final value theorem. Whenever I give you a signal, this is going to be times s evaluated in s equal to 0. In this case, 3. Okay? Perfect. Then we have the gain. For computing the gain, we ladder on the final value theorem. What do? We inject u equals to 1 over s. That is my step. Then I compute my response. That is going to be this one. True. And then I apply final value theorem. That is times s in s equal to 0. H equal to 0. H in 0. Together? They're two slightly different things. Final value theorem, we apply it to a signal. Whenever we apply it for computing the gain, it means that the signal is going to be h times 1 over s. Are we together, people? I see a puzzle face.
Yeah, I just don't get the first part where you multiply by s and then u is 0. Is that for it? Okay.
This is the final value theorem. Okay. I have a signal. I take it in Laplace. I want to compute the limit. How do? Multiply times s, compute in 0. Okay. Then, how do I define the gain? I apply a step. I compute the output. I look at this height. What is this signal here? This is HU, true? Because it's my first response. But actually not that generic U, it's a specific U, it's this U, true? And then if I want to do the final value theorem for this one, assuming that I can do, are we together that we cannot always do that stuff? Are we together that? Assuming that I can do this, I have to do the final value theorem, that means multiply times s and compute in 0. But we are kind of lucky because that s of the final value theorem simplifies the input, that is the specific input that I have, and I remain with stuff here.
The gain is just when you got like a u that is a step two.
Yeah, because it's a delta u delta over
Ah,
delta
that
y.
is
It doesn't matter. Together. Okay. Perfect. No, no. Let's do. Let's do this one. Let's see. How is it going, people? So you would say number 3. This one, is this one stable? No, this one is H that diverges. I excite that system, it's going to diverge, true? So this is a value, this is a number that I can compute, but it cannot be applied as a concept of gain because we don't have Vivo stability. And the gain is only associated to Vivo stability. X. Are we together, people? 1, 2, 3. Excellent.